Okay, in this video, I'm gonna be, this is actually a completely unplanned video, and what I'm doing right now is looking into emulation options on QEMU, the processor emulator, open source, and I'm looking into emulation options for STM32. I've downloaded STM32 version from the Pebble project, which has support for the Pebble board and also the Olimex P103 board, which I am trying to run NuttX on right now. And I've had a few problems. I've had a few registers that were not implemented in that STM32 version, and I had to make a few changes. For example, I had to add in the RCC file. I had to actually comment out some code that corresponds to some RCC registers that were not implemented, like the reset registers, and I just put printf statements there. So when I run the emulator, when I run NuttX on this emulator, I get printouts whenever those registers are being accessed. Now, I still haven't got the NuttX shell, so I decided that I would try to debug what is actually going on, and that's why I'm recording this live, to kind of try and figure out what exactly is happening and why am I not getting the NuttX shell. So let's see if we can actually get this working. I've started QEMU for ARM with machine set to STM32F103 and CPU to Cortex-M3, and as kernel I'm using a NuttX build that is built for STM32F103 CB. And I'm using also the GDB argument that starts a GDB server at TCP port 9000, and that allows me to connect GDB to this QEMU instance, which is right here. This is the QEMU instance that is running this code, and it has it doesn't actually show what it is doing right now. It is just frozen, and I can connect to this instance using GDB. So I call arm non-IABI GDB NuttX. NuttX is the ELF file, which is the source of the binary file that I'm running as the kernel in this emulator, but it contains all of the symbol information, so it allows me to debug it. Now, I start this and I set target remote localhost 9000, and I'm currently sitting in this loop, which is basically wasting CPU cycles. So let's see what this loop does. I press L and I can see that I'm in the upwaste function, so I can go up in the stack and I can see what function has called this upwaste, and it's the RTC wait. And what it's actually doing here is that it's waiting for the RTC register called STM32 control to actually come up. And since this register is probably not implemented, or the RTC is not implemented, it's actually just sitting there and it's not going anywhere. So let's see where this register is in the emulator and see if we can get out of this loop. So I go back to the source of the emulator and I can check if I can find the RTC. So this is the implementation of the RTC on the F2XX board, but we have to make sure that this RTC is actually being used on our board. So I go to F1 and I see if we have an RTC added. And we don't actually even have the RTC peripheral added here. So we might want to do that, or we may want to just make sure that that loop is just not trying to read the RTC status. Let's see if there is any example of the RTC in the Pebble. So Pebble, I think, I'm not actually sure which processor Pebble is using, but we can find out. Let's see. Set QEMU settings. Right, so we have the RTC dev. RTC device is specified to the init function. And the reason I'm a little bit uncertain about this RTC is because this RTC is implemented for 2XX, and I'm not sure if 2XX RTC is the same kind of RTC as is implemented on 10X. So I'm going to see if we can specify an RTC here. So in this init, we don't even specify the RTC. So it seems that RTC needs to be implemented for the 10X architecture, and currently it's not implemented at all. And it's not even, there is nothing that even resembles RTC. So what I'm going to do is simply go into the, let's see, I'm going to go to NuttX. Let's see. I'm going to go to NuttX, and I'm going to look at this function and just disable it. Actually, maybe there is a variable in the menu config that allows me to disable the RTC. So yeah, we can actually do like this. So we go RTC driver support, and watchdog, we can just disable that as well. And then we can just rebuild this NuttX and see if it still hangs. So the goal for this is to actually get a NuttX shell on the serial terminal 0. And obviously the goal after that would be to get the RTC implemented in the emulation environment. So I've compiled the file, and I can just restart QEMU, and I can kill this session, and GDB crashes when that happens. There's some problem with GDB. I mean, it shouldn't really do the core dump thing, but it always does that, even with STM32 debugging. So it's something in the ARM non-IAB GDB that's crashing. Target remote, yeah, remote localhost 9000, and we are sitting in the scheduler. Let's see, are we getting anything here? If scheduler has garbage, and so what are we doing here? Have garbage. Okay. So we're sitting idling there. Now, it's quite likely that this UART is not actually the UART that is connected to UART1. So I'm going to double check that. And I have to find where exactly is the UART. So here we have UART. UART2. So when we are running on the P103 board, apparently we are supplying UART2 as the connection. So we change that to UART1 and see if this works. So UART1. Let's see. STM32 UART. Right. So what this board initialization code does is it calls the STM32F103 init, and it passes the array of UARTs and GPIOs. And the init function initializes these devices, and then you connect. You do this STM32 UART connect, and you connect this UART to the serial descriptor 0. So this should work. This should actually work. So now we have to recompile QEMU. We do make here. And we have compiled the STM32F103, and we can start this again. And let's see if we get a NuttX shell here. Let us see. Yes, we have a NuttX shell. And this is just awesome. That's it. So this is how you get NuttX to work on QEMU STM32F103 version. Thank you for watching, and I hope you learned something.